Hi, for this video, I will introduce the CHSH game with the classic strategy and its winning probability. First of all, Alice and Bob are spatially separated or isolated from each other. For example, Alice lives in Earth and Bob lives in Mars. And in between them, there is Charlie. He's a game referee who decides who win the game. Charlie randomly generate x and y value, which are the random bit numbers, and Charlie send x value to Alice and y value to Bob. Once Alice receives x from Charlie, she decide which a value sent back to the Charlie, and also B decide which B value he sent it back to Charlie. So note that before the game starts, they already have a randomly generated game strategy lambda, so that the lambda, like game strategy lambda, have them to decide A and B values. So once they have A and B, they send A and B to Charlie. So after that, as Charlie has all values x and y and a and b, then he decides who win the game. The winning condition is as follows: x and y is equal to a XOR b is true. Then Alice and Bob win the game. Otherwise, they lose. So before we talk about the winning probability, let's define our indicator function, which returns whenever Alice and Bob win the game. So if this condition is satisfied, this indicator function returns Alice and Bob win, which is 0, and otherwise it returns 1, otherwise it returns 0. So let's talk about winning probability, which is equal to joint probability of x and y, sum of all a and b x and y, this indicator function time this conditional probability of a and b given x and y. Because x and y are randomly generated, they are independent to each other, so that we this joint probability can be written to probability of x times probability y. So probability x is 1/2, and probability y is 1/2, and it becomes a 1/4 chance. And then for the winning probability, we need to analyze this conditional probability, which is important. But to describe this winning, the conditional probability, we also consider to describe the game strategy lambda, which is generated from the random variable lambda that Alice and Bob employ. So by the total probability, and also because random variable takes a continuous value from like a classic or quantum strategies, so we use integral to describe the total probability. Integral conditional probability lambda given x and y, conditional probability of a and b given lambda x and y. But note that the game strategy lambda does not depend on x and y, so we can simplify this conditional probability to probability of lambda. And also a and b are special, Alice and Bob are spatially separated. They act independently, so we can simplify this conditional probability to two probability. probability of A given lambda x and y time probability of B given lambda x and y. But A does not depend on y, so we can simplify to this expression. Also, B does not depend on x, so we can simplify to this expression. So we have this simplified the expression of this conditional probability, but note that any stochastic map probability of A given lambda x or probability of B given lambda y can be simulated by applying deterministic binary value function f to a local random variable n. I think n is local, m is local hidden variable at Alice's location and Bob's location. So whenever Alice decides a value given lambda game strategy x from Charlie and also some local hidden variable, then this f function returns 1, otherwise 0. So whenever Alice decides this function, f function gives, she decides true 1, otherwise 0. Similarly, we can define redefine this conditional probability to g function. So by g, this determines a binary value function g. So we rewrite this conditional probability to this expression, the integral probability of n times f of A given lambda x and n, and probability of B given lambda y is equal to integral probability of n times g B given lambda y and n. So by the discussion for this conditional probability, we have this new expression. But as we think about random variable lambda include the local random variables n and m in each one's location. So we can just simplify this expression to f prime and g prime, were also governed by this random variable lambda. So we have simplified the expression for this condition probability. So with this expression, now we can analyze more of the winning probability. So by discussion so far, we have this expression. This expression is substitutes for this conditional probability, and some algebra we have this expression, which is the average of winning probability of all game strategy. But as we know, maximum is always greater than average. So we have this new expression, f prime A given lambda star x times g prime B given lambda star. So we need to find the maximum game strategy. So we can write down all game scenario. So for example, x value can be 0 and 0 and 1 and 1, and y value from the Charlie can be 0, 1 or 0 or 1. So the x and y can be 0, 0, 0, 1, and also this is all A XOR B value from Alice and Bob. So just think about when they can win the game, just maximally with the maximum game strategy. So if they have, suppose if they have game strategies, whenever they have X and any X and Y value, just Alice and Bob return same value, 0, 0, 0, or 1, 1, 1, 1. So in that case, they can win the game 3 out of 4 because this, suppose Alice and Bob sends same value 0. This is 0, and as this becomes 0 and 0 and 0, they only lose this condition because this is 1. Oops. So 3 out of 4, the Alice and which is the maximum winning probability of the CHSH game, which is 75%. Okay, thank you for listening. Bye.